Okay, this is actually lecture 7C, sorry for the typo at the top there. In this lecture we are going to find scores between which a certain proportion of a normal distribution falls. The key word there being finding the score this time rather than finding the proportion. And finally, finding the number of scores associated with a particular proportion. And so that would be if we had, say, 1,000 people, how many of those people fit the requirements for a certain proportion. Okay, the first example I want to work is actually an awful lot like the ones from lecture 7B. Let's look at golf, frisbee golf, where it takes 27 throws on average to complete a course, and the standard deviation is about 4. So if 27 is the mean, I need to add 4 consecutively to get the standard deviations to the right and subtract 4 to get the standard deviations to the left. Then I want to continue reading the problem. I want to know what proportion of the population would be expected to score 22 or less, 22 being what's par for the frisbee golf course. So I mark off where 22 would be on my number line, and I realize or less is that I want the tail. The tail is column C in table C in Spatz. I'm expecting to calculate a z of somewhere around, I don't know, 1.2-ish, just based off of my estimation from my drawing. And so I would also estimate my answer to be something less than 16%, so probably somewhere around 12-ish%. Calculating a z-score, take your score of interest minus the mu. The score of interest is 22, minus mu, which is our mean, 27, divided by the standard deviation of 4. Gives you negative 5 over 4, or 1.25, negative 1.25, just to remember where we are on the curve itself. We're lower than the mean. I've planned ahead, and there's 1.25, and I want column C, so that means that the area to the left of that bar is 0.1056. Now, I thought my estimate was a little bit high. I estimated, what, 12%, something like that. So it's still a reasonable answer, about 0.11-ish of the population, that's the proportion of the population, would be expected to score a 22 or less. So those would be the guys and gals who are in the lead, who are winning. All right, part B, same background. Now I want to do another kind of review problem and look at the proportion between two scores. And the two scores I'm interested in are fairly close by, so I'm not even going to bother setting up the whole curve. I'm just going to set up the part that, that really matters for this part of the problem. So 25 would be to the right of 23, and 30 would be a little bit to the left of 31. And I see that I've really got two chunks here if I use the middle as a dividing line, and both of those chunks are going to correspond to areas on table C in column B, and remember B is near the bump. So I need to calculate two z-scores and find two areas from column B and then add them together to get the area in between 25 and 30. So for the z-score of 25, take the score of interest, 25, minus the mean, 27, divide by the standard deviation of 4, and you get negative 2 over 4, which is negative 0.5. Now remember, I want column B, so 0.5, because the sign doesn't matter on the table. You just have to be careful about which column you're choosing, is 0.1915. 0.1915 seems reasonable because I know that the whole chunk is 34%. 19% seems about right for the larger half of the chunk, meaning the half that's closer to the center. So I'll go ahead and label that in, 0.1915. Remember, it uses a z-score to find the area, and then you deal with the areas. A z-score of 30, 30 minus 27 over 4, gives me 3/4, that's not a negative sign, by the way, it's just a smudge on my paper, and I have 0.75, again column B is 0.2734, that makes sense, it should be larger because the line for 30 is closer to the first standard deviation. And to find the total proportion between these two, I just need to add the little suckers up. And a little bit of mental math, 0.1915 plus 0.2734, and I get 9, 4, 6, carry the 1, 4, and that is 0.4649, sorry, or approximately just under half of all of the competitors would be expected to score between 25 and 30. Some of them below the mean and some of them above. Makes sense. Tall part of the curve, 46%, seems reasonable. Problem C is new. This is really addressing the objectives for 7C. Now what I want to do is not just talk proportion. I want to actually figure out how many people. So to do that, you need to know two things. You need to know what the proportion is pertaining to the conditions you've given, and you need to know how many total people you're talking about, N. So in this problem, I'm going to have a 950 student competition class going at this Frisbee golf course, and I'm curious about those who were extremely good, the creme de la creme of Frisbee golf. So I'm interested in the tail region because I'm looking for a score of 20 or less, because those lucky golfers are going to get some sort of a prize, like, I don't know, a Frisbee. So find your C-score. 20 minus 27 is over 4. I have no idea why I wrote -3. Ay, can you tell I haven't been getting enough sleep? Let's see, I think I fix it. Oh, yes, I do. 20 minus 27 is -7. So my z-score is -1.75. And it's a good thing that I caught that. And I didn't even make a prediction this time. I probably should have. So column C, because I just want that tail region. Sorry about my dogs there. 0.0401 times 950 students, so that's a proportion times the number of competitors in this case, and you get 38.09 and change. Well, it'd suck to be the 0.09 of a person, so we always round up when we're talking about actual subjects or participants or, you know, things that are only counted in one unit at a time. So you better plan for 39 prizes, maybe 40, just in case you have a particularly good crop that year. Alright, blank screen. The blank screen is because I want to show you a little bit of algebra. Sorry, I start saying things funny when I'm tired. What I want to do and what's happening on the screen here is I'm showing that I'm solving the equation that we've been using for z, and I'm going to actually solve it for x, because in the next set of problems we're going to be looking for the value x that corresponds to a certain z. So I started by getting the sigma out by multiplying both sides of the equation by sigma, and now I'm getting the mu away from x by adding because it was subtracted. And I get the answer, which is the x, the score of interest, can be found by taking the value of z times the standard deviation and adding it to the mean. With that in mind, let's go on to the next question. In this next question, an experimenter wants to find some very good and very bad Frisbee players. Not quite sure why, but hey, it could happen. She wants to use the top 10% and the bottom 10% of the competitors. So I've tried to mark off here approximately 10%, remembering it's 214. So it's not going to be to the second standard deviation from the left or to -1 yet. So I've kind of marked it off, and I realized that I want a z-score that's probably going to be somewhere around plus or minus 1.2-ish, based off my estimation in the drawing. So how do we actually figure it out? Well, I've got to look at that for that area and find the z that corresponds to it. If I'm working with a tail, that's the column C. And for 10%, the proportion is 0.1000. So looking along column C, I want to find the proportion that is closest to 0.1003. Closest is all we care about. And I see that that comes from a z-score of 1.28. Really, either plus or minus 1.28. So I used the context in the problem to figure out the proportion that mattered, and then I went to the table in the right column, found that proportion, and looked to column A to see the z-score. Now here comes our new equation, x equals z sigma plus mu. So the x is what we're looking for. It's the z, 1.28, times sigma, which is 4, plus the mean, 27, is the average, remember, to get through the course itself. If we solve for that, it'll give us the actual mark-off line, the cutoff score for, in this case, the worst Frisbee golfers, because a lower score means that you're good and a higher score means that you're bad, or just not as good. Probably better than me. So anyway, the cutoff score appears to be 32.12, and since there are no proportions, we'll just say 32. Now what I need to do is I need to calculate it to the left of the mean. So I'm going to take the mean, 27, and this time I'm going to subtract 1.28 times 4. And that gives me 21.88, which means that a score of 22 or lower would mark off the top 10% of golfers. So not quite sure what I was trying to write there. Lower than 22 or higher than 32 would be the competitors whom the researcher recruits for whatever the study is of Frisbee golfers. Okay, let's move on to the next example. This time we'll work with something a little more serious, SAT scores. Lots of people take the SAT every year, so when they actually plot the distribution, it turns out normal on its own. So it's an example of an empirical distribution that acts like a theoretical distribution also. With a mean of 503 and a standard deviation of 113, this normal distribution can be set up by just using a standard curve. Now, in this particular problem, we're interested in the students who took this test who scored a 500 or above. So the green line indicates where a 500 would be if the mean were 503, and above means I'm shading the area to the right. I'm anticipating this to be just a little bit more than 50% of the students have scored this high. Now, I could do this a couple ways. I could find column B and add it to a half, or I could find column C and subtract it from 1. So that's what I'm going to try, just to kind of mix it up a little bit. So we're going to find a z-score for our value of interest, 500. Then we're going to use column C, which is actually to the left, and take that chunk out of the entire normal curve by taking 1 minus that proportion to get the green shaded region instead. So 500 minus 503 over 113 equals -3 over 113, which gives me really a very small number of -0.0265. Now the table only uses z-scores to 2 decimal places, so I'm just going to go ahead and round that. And I have my table all ready for us, and remember I've decided to take the tail. So that means that the unshaded region on the green curve, which corresponds to the blue shaded region on the left there, is 0.4880. To find the part I care about, which is those scoring 500 or above, I'm going to take 1 minus that number. And 1 minus that number gives me the proportion 0.512, which does make sense because we said it would be just slightly more than 50%. So if you're an admissions director, say you've learned that students who don't do well on the critical reading portion of the SAT exam tend to not do well at your university. Maybe they just don't have the preparation needed. So what I want to do is I want to estimate where the lowest 20% of those SAT scores are, and I'm just going to eliminate them from the admissions pool. So, they get so many applicants that eliminating some at the beginning can actually be helpful in making the process a little less painful for them. So what I've done is I've shaded what I would perceive to be approximately 20% of the curve, knowing that I've got 214 and then a little bit more. 20% expressed as a proportion is 0.200, and looking down column C, because it's the tail, I see that 0.2005 is the value closest to 0.2000. If there's like one that straddles it and there's just slightly different, take the one that's closer. If they're exactly the same, just choose one, and it won't make that big of a difference in the long run. So if z equals 0.84, and important, it's negative 0.84 because it's to the left of the mean. And that negative becomes really important because I need my score to reflect that it's lower than the mean. And by having negative 0.84 times the standard deviation, so z times sigma, plus the mu, that first term, z sigma, will be negative, meaning the value for x will be less than the mean. Very, very important. Otherwise, you'll be isolating the top 20% of all scores and not the bottom. So working the math in my calculator there, not going to lie, I totally cheated on that one. I end up with an x value of 408. And that means that the cutoff score the university should consider is that they're not going to take any applicant with a score lower than 408. I imagine they probably wouldn't take a 408 either, because they would look at everything else, and if that person was great in other areas, maybe consider him. Okay, next part, what we want to do now is we want to look at the difference between a 99th percentile, which is awesome, and a 99.9th percentile score, which is phenomenal. There's a huge difference in terms of what a person would actually have to achieve to move from the very, very amazing 99th percentile to the phenomenal 99.9th percentile. My lines there might be a little bit off, but I wanted to kind of exaggerate it a little bit for you. So 99th percentile, you got to be careful. It means it's a proportion of 0.99 or 0.9900. That's what separates the 99% of the area on the left from it on the right. And that means that the tail would be just this teensy little bit, 0.01, because if you take 0.01 and add it to 0.99, you'd get a whole, 1.00. So looking along column C, you'll see that the z value of 2.33 is what corresponds to a z-score that gives the tail area to be closest to 1% or 0.01 as a proportion. Repeat this process for the 99.9th percentile, and what's different is a power of 10 in terms of where you're looking. Instead of 0.01, you want 0.001. And you can see there we're all the way past the third standard deviation, which we don't talk about much because it's so rare. And 0.0010, you see there are actually 3 choices there. Just choose one. I tend to choose like the first one I see. It doesn't really matter. And you'll see why here even more so in a second. If you have a z-score of 3.08, that would place your score in comparison to the rest in the 99.9th percentile. Now I erased that because I'd scribbled too much, but let's re-put in that information. I had 2.33 for the 99th percentile and 3.08 for the 99.9th percentile. Now I want to finish the problem and answer the question, what score? What score means you've got to have x equals. X equals z sigma plus mu. I remember that I just found the z's. Sigma is 113 and mu is 503. So I'm going to do two of these equations, the first x being for the z-score corresponding to the 99th percentile, and that means it's a 2.33 times the standard deviation of 113 plus the mean, 503, and that gives you an exceptionally good SAT score, given that it's reported to 800 as a perfect score. We'll talk about that in a second. But it gives you an exceptional z-score once you multiply and then add your terms of a 766. They don't do SAT scores with decimals, so 767 would definitely ensure that the person was in the 99th percentile. Kind of splitting hairs though. 766, 767, pretty much the same thing. For the 99.9th genius, we have 3.08 times 113 plus 503. That first term, instead of being 263 when you multiply them, is now a lot higher at 348. Add that to 503, and now suddenly this kiddo has blown the top off the SAT and scored an 851. And an 851, believe it or not, is actually possible when the testing center is scoring them. But for the sake of the statistics, they actually only report the SAT from 200 to 800. That means that you could put your name on the thing, answer no questions, and it would be reported as a 200. Because they're not going to report something lower than that. Same thing with an 800. And I always get a kick out of this because I've had a few students in my past score 800s. And they're like, oh, I scored a perfect score. I'm like, you actually don't know that. Because it is reported to a higher score than what they show as being possible. So, kind of a little bit of a buzzkill for them, but they deal. Problems D and E, so the last two for this guy. Now it's going to be one of those how many students questions. So if I had 1,000 randomly selected students, that's important actually, randomly selected from the population, students, how many of those students would be expected to score a 700 or more? So let's set up the actual curve. So I'm taking the time to do the math here. I take my mean and I add my standard deviation successively so that I can mark off so that I encompass my score of interest of 700. And I estimate where that is and shade the region I care about, the region being or more, so to the right. That's the tail, so I'm going to be looking at column C. And I want a column C value, and it's going to end up being where I need the proportion and the number of students. So I go back to doing just a regular z-score calculation. 700 minus 503, all divided by 113. Now it's important to do the subtraction, hit enter, and then your division. Otherwise, the order of operations will do the division before the subtraction. You'll get a very wrong answer. Anyhow, do that and you get a value for z of 1.74, and that doesn't round because the next number isn't a 5 or higher. Look up 1.74 and the tail region is around 4% or 0.0409. So the z of 1.74 corresponds to a probability or proportion, probably more appropriately called a proportion of 0.0409 of students who overall scored a 700 or higher. From my 1,000 randomly selected students, what proportion of, or how many students would we expect to actually score that or higher? We're going to multiply. 3 zeros in 1,000 means move your decimal 3 places to the right. And you get a very small number. About 41 of those students could be expected to have a 700 or higher. Obviously, if you chose these students from a non-representative sample, if it was non-representative of the population, that wouldn't be valid. I mean, if you took 1,000 prep school kids and compared it to this problem, I'm sure there would be more students just because of the demographics of the prep schools that would have the 700 or higher. Alright, to segue on my last silly example from Star Wars, let's talk about those little Jawas again. Same idea that they're 4 feet tall with a standard deviation of 3 inches. But in this scenario, there's some sort of craziness happening on with the head Jawa, who thinks that the extreme heights of his population are bad. And so he's taking the super extreme 5%, which means 2% on 2.5%, on either side, and what's the word I'm looking for? And banishing. There it is. Banishing them to a different planet. So the question then, of course, becomes for the head Jawa or his administrative assistant, whoever that might be, is, well, just how tall is too tall and just how short is too short? So the tails of 2.5% means that they correspond to a proportion of 0.025. And remember, all we do there is we're dividing by 100 to take it out of a percent and into a proportion, just like we multiply by 100 to go from a proportion to a percent. So we're looking for the column C, the tail part of the column, that has a 0.0250 proportion, and that corresponds to a z-score of 1.96. So on the right hand side that would be a positive 1.96, and on the left hand side that would be a negative 1.96. If we're answering the question what height, or what score generically, what height is going to give us the extreme 5%, 2.5 on top and 2.5 on bottom, what we need to do is 2x calculations, where x is equal to z sigma plus mu. When the value is above the mean, remember we have to ensure we're using the positive z, so that it ends up getting larger than the mean. So you can write it mu plus sigma z, mu plus z sigma, or sigma z plus mu, or z sigma plus mu. All of those possible combinations are just fine because of the way math works. So I can say 48 plus 1.96 times 3 being the standard deviation, 48 being the mean expressed in inches. And I end up with an extreme tall height of 53-ish inches, 53.88 inches. I just got this image of a Jawa holding up a meter stick or a yardstick and measuring in inches. Oh my. If the value is below, you're going to have to subtract. And the subtraction is taken care of by using the negative z-score. So using negative 1.96 instead of positive means we end up subtracting, because a positive times a negative is a negative. So in our next calculation, we expect the value to be equidistant from the mean to the left as the 53.88 was to the right. Let's see, what did I write there? The negative is covered by the negative z, basically what I just explained. So as long as you're careful with the z being positive or negative appropriately, and using the equation consistently as a plus in between the mu and the z sigma term, you'll be fine. So mu minus z sigma, the minus happens so that it goes to the left, and that minus is accounted for, again, for the 15th time this lecture, by the negative sign. Alright, so our second x is going to be equal to 42.12. So the super shorty Jawas, the ones that get banished with the super tally Jawas, are going to be 42.12 inches or shorter. So they'll ship them off to Alderaan, and they'll get to ride around in their sand crawlers and hopefully not have to duck when they crash. Okay, so shorter than 42 inches and taller than 53 inches, 54 inches, yeah, 54 makes more sense because of rounding, will be the unlucky little guys and tall guys that get to go bye-bye. And finally, because there were 600 Jawas, 5% of that is 0.05 times 600, or 30. So really, they're only banishing about 30 of their tribe, pack, civilization, whatever you want to call it.